The moons of our solar system. A journey through alien worlds. Chapter 1. Worlds beyond worlds. In the vast expanse of our solar system, 8 planets orbit our Sun. But they do not travel alone. Accompanying them on their cosmic journey are over 200 natural satellites, worlds we call moons. These celestial companions come in remarkable variety. Some are larger than planets. Others are no bigger than mountains. Some harbor hidden oceans beneath icy shells. Others are volcanic infernos, constantly reshaping their surfaces. And a few may hold the very ingredients necessary for life. Tonight, we embark on a journey to explore these alien worlds. We'll travel from the familiar surface of our own moon, to the methane lakes of Titan, to the volcanic fury of Io, and to mysterious ocean worlds that may harbor life beneath kilometers of ice. The story of moons begins over 4.5 billion years ago, in the early chaos of our solar system's formation. As planets coalesced from the swirling disk of gas and dust surrounding the young sun, moons formed alongside them through several different processes. Some moons formed from the same disk of material that created their parent planet, spinning out from the same cosmic nursery. Others were captured wanderers, asteroids that strayed too close to a planet's gravitational embrace and became permanent companions. And some were born from catastrophic violence, debris thrown into orbit by massive collisions. Our own moon belongs to this last category. Its origin story is one of destruction and creation on an unimaginable scale. Before we venture to the distant moons of the outer solar system, we begin our journey close to home. We start with the one moon humanity knows best, the one that has inspired countless generations to look up at the night sky in wonder. We begin with Earth's moon. The moon has been our companion for over 4 billion years. It lights our nights, drives our tides, and has been a constant presence throughout the entire history of life on Earth. Ancient humans tracked its phases to measure time. Poets wrote verses to its beauty. And in the summer of 1969, humans finally stood upon its surface. But the moon's story begins in violence and fire. Let us travel back to the very beginning, to understand how this magnificent companion came to orbit our world. Chapter 2. The Moon, Earth's ancient companion. 4.5 billion years ago, the young Earth was a very different place. The planet had only recently formed, and the solar system was still a chaotic realm of colliding worlds and debris. Earth had been growing through countless impacts, each collision adding mass and generating tremendous heat. Then came the impact that would change everything. A Mars-sized object, sometimes called Theia, was on a collision course with Earth. The impact was not head-on, but struck at an angle, a glancing blow that would prove crucial to what followed. When Theia collided with Earth, the energy released was beyond comprehension. The entire surface of Earth became molten. Massive amounts of material from both worlds were vaporized and thrown into space. This superheated debris formed a ring around Earth, a glowing disk of vaporized rock and metal. Over time, this material began to cool and coalesce. Within perhaps only a few hundred years, the debris had gathered together under its own gravity, forming a new world in orbit around Earth. The moon was born. This violent origin explains many of the moon's peculiar characteristics. It explains why the moon has a relatively small iron core compared to its size. Most of the iron from both worlds sank into Earth's core, while the moon formed primarily from the rocky mantles of the two colliding planets. It explains why rocks returned by the Apollo astronauts are so similar in composition to Earth's crust. And it explains why the Moon is so large relative to its parent planet, a proportion unusual in our solar system. In those early days, the newly formed Moon orbited much closer to Earth than it does today, perhaps only 20,000 kilometers away, compared to the current distance of 384,000 kilometers. From Earth's surface, it would have appeared 15 times larger in the sky, a massive sphere dominating the heavens. The Moon was also spinning much faster, and Earth's day was only about 5 hours long. But gravitational forces between the two worlds created tidal bulges, gradually slowing the Moon's rotation and pushing it farther away. Over billions of years, the Moon became tidally locked, always showing the same face to Earth as it continues to slowly recede at about 4 centimeters per year. The surface we see today tells the story of billions of years of impacts. The bright highlands are the Moon's original crust, formed when lighter minerals floated to the surface of the Moon's early magma ocean. These heavily cratered regions are ancient, dating back over 4 billion years, and they record the intense bombardment of the early solar system. The dark patches we call Maria, Latin for seas, tell a different story. These are vast plains of volcanic basalt that flooded low-lying regions between 3 and 1 billion years ago. Ancient astronomers thought they were actual seas of water, hence their poetic names like the Sea of Tranquility or the Ocean of Storms. But they are bone-dry, airless expanses of ancient lava flows, frozen in time. The largest of these impact features is the South Pole Aitken Basin on the Moon's far side. This immense crater is over 2,000 kilometers across and 13 kilometers deep, one of the largest impact structures in the entire solar system. The collision that created it must have nearly shattered the Moon, excavating material from deep within the lunar interior. Today, the Moon is a cold, airless world. Without an atmosphere to redistribute heat, temperatures swing wildly from 127 degrees Celsius in direct sunlight to minus 173 degrees in shadow. Its surface is covered in regolith, a layer of pulverized rock and dust created by billions of years of micrometeorite impacts. But recent discoveries have revealed that the Moon still holds surprises. Deep craters at the lunar poles, regions that have not seen sunlight for billions of years, contain water ice. These permanently shadowed regions are some of the coldest places in the solar system, cold enough to trap water delivered by ancient comet impacts. This ice may prove invaluable for future lunar explorers, providing both drinking water and rocket fuel. The Moon also preserves a unique record of Earth's history. Because the Moon has no atmosphere or plate tectonics, its surface is a time capsule. Ancient asteroid impacts on Earth that left no trace on our geologically active world may still have left evidence on the Moon's unchanging surface. The lunar regolith even contains particles blown off Earth's atmosphere by the solar wind, a 4 billion-year archive of our planet's atmospheric evolution. As we prepare to leave our Moon and venture to the moons of Mars, we carry with us an appreciation for this ancient companion. The Moon has witnessed the entire history of life on Earth, from the first single-celled organisms to the moment humans finally reached up to touch its surface. It has been a constant presence, a beacon in our night sky, and perhaps a stepping stone to the stars. But the Moon, for all its majesty, is only the beginning of our journey. Ahead of us lie worlds even more exotic and mysterious. Our next destination, the red planet Mars, and its 2 small, dark companions. Chapter 3. Phobos and Deimos, Mars' mysterious companions. Mars, the red planet, has two small moons that have puzzled astronomers since their discovery. Named Phobos and Deimos, Greek words meaning fear and panic after the sons of the war god Ars. These tiny worlds are unlike Earth's moon in almost every way. They were discovered in 1877 by American astronomer Asaph Hall, using the United States Naval Observatory's 26-inch refractor telescope. Hall had been searching for moons of Mars for several nights and was about to give up when his wife, Angeline, encouraged him to try one more night. That final attempt revealed first Deimos, the smaller outer moon, and then Phobos 6 nights later. Phobos, the larger and inner of the two moons, is only 27 kilometers across at its widest point, roughly the same size as a small city. Its surface is dominated by an enormous crater named Stickney, after Angeline Stickney Hall. This impact crater is 9 kilometers across, nearly half the width of Phobos itself. The collision that created Stickney must have come close to shattering the entire moon. The impact sent shockwaves through Phobos, creating a pattern of strange grooves that radiate across its surface. These grooves, some of them hundreds of meters wide and tens of meters deep, were likely formed as the violent shaking from the Stickney impact fractured and cracked the moon's interior. Phobos orbits Mars at an altitude of only 6,000 kilometers, making it the closest moon to its planet in the entire solar system. It completes an orbit in just 7 hours and 39 minutes, faster than Mars rotates. This means that from the surface of Mars, Phobos rises in the west and sets in the east, crossing the sky in just 4.5 hours. An observer on Mars would see Phobos rise and set twice in a single Martian day. But Phobos is living on borrowed time. Tidal forces are gradually slowing its orbit, causing it to spiral slowly inward toward Mars. In about 50 million years, Phobos will cross below the Roche limit, the distance at which tidal forces overcome the moon's own gravity. When that happens, Phobos will be torn apart, potentially creating a ring system around Mars that could last for millions of years. Deimos, the smaller and more distant moon, orbits at 23,000 kilometers from Mars. It is even tinier than Phobos, only 15 kilometers across, shaped like a lumpy potato. From the Martian surface, Deimos would appear only slightly brighter than Venus appears from Earth, a slow-moving star rather than a moon. Unlike Phobos, Deimos orbits just beyond synchronous orbit, meaning it rises in the east and sets in the west like Earth's moon. However, its orbit is so slow that it takes 2.5 Martian days to cross the sky from horizon to horizon. To a human observer on Mars, Deimos would barely seem to move, hanging almost stationary in the sky for hours. Both moons are covered in a thick layer of fine dust, giving them an unusually smooth appearance compared to similarly sized objects. This dust, called regolith, is likely the result of billions of years of meteorite impacts pulverizing the surface. The dust makes both moons appear darker than charcoal, reflecting only about 6% of the sunlight that hits them. The origin of Phobos and Deimos has been debated for decades. They resemble asteroids in many ways. Their dark surfaces, irregular shapes, and low densities are similar to carbonaceous asteroids from the outer asteroid belt. This led many scientists to propose that they were asteroids captured by Mars' gravity billions of years ago. However, this explanation has problems. Captured asteroids typically end up in elliptical or inclined orbits. But Phobos and Deimos circle Mars in nearly perfect circular orbits aligned with the planet's equator, more consistent with moons that formed in place alongside Mars. Recent research has suggested a third possibility, one that combines elements of both theories. Perhaps Phobos and Deimos are the remnants of a much larger moon that once orbited Mars. This moon may have formed from debris thrown into orbit by a massive impact early in Mars history, similar to how Earth's moon formed. Over time, tidal forces caused this moon to spiral inward until it was torn apart by Mars' gravity, with Phobos and Deimos being the surviving fragments that ended up in stable orbits. Future missions may finally solve this mystery. The Japanese Aerospace Exploration Agency's MMX mission, planned for launch in the coming years, aims to visit both moons and return samples from Phobos. These samples will reveal the composition of the moons and potentially settle the question of their origin once and for all. For now, Phobos and Deimos remain enigmatic. These small, dark worlds bear silent witness to Mars' history, having orbited the red planet for billions of years while it transformed from a warm, wet world to the frozen desert we see today. As we leave Mars behind and journey outward into the solar system, we cross a boundary. Beyond Mars lies the asteroid belt, and beyond that, the realm of the giant planets. Here, gravity is king, and moons are counted not in ones or twos, but in dozens. Our next destination is the largest planet in the solar system, home to a system of moons so diverse and fascinating that they constitute a miniature solar system unto themselves. We travel now to Jupiter, king of planets, and its magnificent family of moons. Chapter 4. Io, the Volcanic Inferno. As we leave Mars and journey across the asteroid belt, we enter the realm of Jupiter, the king of planets. Jupiter's immense gravity has captured at least 95 known moons, but 4 stand out as truly exceptional. These are the Galilean moons, discovered by Galileo Galilei in 1610, when he turned his primitive telescope toward Jupiter. That discovery 400 years ago was revolutionary. For the first time, humanity observed objects clearly orbiting another world, powerful evidence that not everything in the cosmos revolved around Earth. Galileo's 4 moons, Io, Europa, Ganymede, and Callisto, would prove to be worlds as diverse and fascinating as the planets themselves. We begin with the innermost of these moons, a world that defies everything we thought we knew about moons. We begin with Io. Io orbits Jupiter at a distance of 422,000 kilometers, completing one orbit every 42 hours. It is almost exactly the same size as Earth's moon, 3,600 kilometers in diameter. But any similarity to our moon ends there. Io is the most geologically active body in the entire solar system, a world being continuously torn apart and rebuilt by volcanic fury. When the Voyager 1 spacecraft flew past Io in 1979, scientists expected to see a cold, dead world, cratered and ancient like Earth's moon. Instead, the images revealed a surface unlike anything ever seen, painted in brilliant yellows, oranges, reds, and blacks. There were almost no impact craters. And then, in one of the most stunning discoveries in the history of space exploration, navigation engineer Linda Morabito noticed something strange in one of the images. A bright plume extended hundreds of kilometers above Io's surface. Io had active volcanoes. Not just one volcano. Io has over 400 active volcanic centers across its surface, erupting continuously. At any given moment, dozens of eruptions are in progress. These are not gentle lava flows. Some of Io's volcanic plumes shoot material 300 kilometers above the surface, higher than the orbit of the International Space Station above Earth. The volcanoes of Io are powered by heat, tremendous amounts of heat generated in the Moon's interior. But this heat does not come from radioactive decay like it does on Earth. Io's internal fire is created by something far more violent: tidal forces. Io is locked in an orbital resonance with Europa and Ganymede, Jupiter's other large moons. For every orbit Io completes around Jupiter, Europa completes exactly 2 orbits, and Ganymede completes exactly 4. This precise mathematical relationship creates a gravitational dance that constantly tugs on Io, preventing its orbit from becoming perfectly circular. As Io moves closer and farther from Jupiter in its slightly elliptical orbit, Jupiter's immense gravitational pull flexes and kneads the Moon like a stress ball. The interior of Io is constantly being squeezed and stretched, generating friction and tremendous heat. This process, called tidal heating, raises and lowers Io's surface by as much as 100 meters during each orbit, creating enough internal heat to melt rock. The result is a world of endless volcanic activity. Lava flows reshape Io's surface constantly, covering any impact craters almost as soon as they form. Some volcanic features are massive calderas hundreds of kilometers across. Others are towering mountains of sulfur and rock, some reaching heights of 17 kilometers, taller than any mountain on Earth. The largest volcanic feature on Io is Loki Patera, a volcanic depression over 200 kilometers across containing a massive lava lake. The surface of this lake periodically overturns in waves, releasing enormous amounts of heat in eruptions that can be detected by telescopes on Earth, nearly 600 million kilometers away. A single eruption from Loki Patera can release more heat than all of Earth's volcanoes combined. Io's volcanoes don't erupt water or carbon dioxide like icy moons. They erupt molten rock and sulfur compounds. The surface temperature around active volcanic vents can reach 1500 degrees Celsius, hot enough to melt rock into glowing rivers of lava. Some of these lava flows are made of ultramafic magma, a type of extremely hot lava not seen on Earth for billions of years. The volcanic activity has another dramatic effect. Io has a thin atmosphere, but it is an atmosphere constantly being created and destroyed. Sulfur dioxide gas erupts from volcanoes, creating a temporary atmosphere that extends several hundred kilometers above the surface. But Jupiter's radiation is so intense that this atmosphere is constantly being stripped away, ionized by radiation and swept off into space by Jupiter's powerful magnetosphere. This creates a vast cloud of sulfur and oxygen ions that stretches along Io's orbit, forming a torus, a donut-shaped cloud of plasma that circles Jupiter. This Io plasma torus glows faintly in ultraviolet light and plays a crucial role in Jupiter's powerful auroras. Material from Io's volcanoes ultimately rains down onto Jupiter's upper atmosphere, creating bright auroral displays near the planet's poles. The surface of Io is one of the most hostile environments imaginable. The radiation near Jupiter is lethal. A human standing unshielded on Io's surface would receive a fatal radiation dose in minutes. The temperature swings from -160 degrees Celsius in shadow to 1500 degrees near active volcanoes. The atmosphere is so thin it is essentially a vacuum, and the ground itself is constantly being recycled, with volcanic eruptions burying and transforming the surface at a rate of about 1 centimeter per year. Despite these extreme conditions, or perhaps because of them, Io has taught us valuable lessons about planetary geology. Its continuous volcanic activity is a window into processes that shaped rocky planets billions of years ago. The same tidal forces that torture Io may operate in more subtle ways on other moons throughout the solar system, including some that may harbor life beneath their icy shells. Io also demonstrates the incredible diversity of worlds in our solar system. A moon almost identical in size to our own moon is a hellscape of active volcanoes, reshaped continuously by gravitational forces, painted in surreal colors by sulfur compounds, bathed in lethal radiation. It is a reminder that the universe is far stranger and more wonderful than we ever imagined. As we leave Io behind, moving outward from Jupiter, we journey to a world that could not be more different. Where Io is fire, our next destination is ice. Where Io's surface is continuously renewed, our next destination has a surface that may be millions of years old. And where Io is utterly hostile to life, our next destination may be one of the most promising places in the solar system to search for extraterrestrial organisms. We travel now to Europa, the ice-covered ocean moon. Chapter 5. Europa, the ice-covered ocean world. Europa orbits Jupiter at a distance of 670,000 kilometers, about 50% farther from Jupiter than Io. It is slightly smaller than Earth's moon, with a diameter of 3,100 kilometers. But beneath its frozen surface, Europa may hide the largest ocean in the entire solar system. From a distance, Europa appears as a brilliant white sphere, one of the brightest objects in the solar system. Its surface is almost pure water ice, reflecting sunlight like a giant cosmic mirror. But as spacecraft have drawn closer, they have revealed that this ice is far from smooth and pristine. Europa's surface is covered with strange features that hint at the dramatic processes occurring beneath. The most striking characteristic of Europa's surface is its relative lack of craters. While most moons and planets in the solar system are heavily scarred by billions of years of impacts, Europa has very few craters. This tells us that the surface is young in geological terms, perhaps only 20 to 180 million years old. Something is continuously renewing Europa's surface, erasing the record of ancient impacts. That something is ice. Europa's surface is a shell of water ice 15 to 25 kilometers thick, floating on top of a liquid ocean that may be 100 kilometers deep. This ocean contains more water than all of Earth's oceans combined, despite Europa being much smaller than our planet. How do we know this ocean exists when we cannot see it directly? The evidence comes from multiple sources. Europa's density suggests it has a rocky interior surrounded by water. Magnetic field measurements by the Galileo spacecraft revealed electrical currents consistent with a conducting fluid beneath the surface, most likely salty water. And the surface features themselves tell a story of an ice shell constantly being fractured, moved, and renewed by the liquid ocean below. The surface of Europa is crisscrossed by thousands of dark linear features called lineae, cracks in the ice that can stretch for thousands of kilometers across the moon's surface. Some of these cracks are relatively fresh and clean, bright ice exposed where the surface has recently fractured. Others are stained reddish-brown by material that has welled up from below or been altered by Jupiter's intense radiation. The most dramatic surface features are called chaos terrain, regions where the ice shell appears to have completely broken apart and reassembled in a jumbled mess. Large ice blocks, some tens of kilometers across, have been rotated, tilted, and moved, like a jigsaw puzzle that has been taken apart and put back together incorrectly. These chaos regions suggest that the ice shell is relatively thin in places, perhaps only a few kilometers thick, allowing the liquid ocean below to break through and disrupt the surface. Scientists have also identified features that may be ice volcanoes, places where liquid water from the ocean below has erupted onto the surface. High-resolution images show what appear to be flows of materials spreading across the surface, and some features resemble frozen plumes where water erupted into the vacuum of space and immediately froze, falling back to the surface as snow. Recent observations using the Hubble Space Telescope have detected what may be plumes of water vapor erupting from Europa's south polar region, shooting 100 kilometers or more above the surface. If these plumes exist, they would provide a way to sample Europa's ocean without having to drill through kilometers of ice. A spacecraft could simply fly through a plume and collect water samples directly from the ocean below. But what keeps Europa's ocean liquid? At Jupiter's distance from the Sun, water should be frozen solid. The answer, once again, is tidal heating. Like Io, Europa is locked in orbital resonance with the other Galilean moons. As it orbits Jupiter, gravitational forces flex and bend Europa's interior, generating heat through friction. While this tidal heating is much less intense than on Io, it is enough to keep the ocean liquid beneath the ice. The ocean itself is likely in contact with a rocky seafloor. Water interacting with rock could create chemical energy, the same kind of energy that powers ecosystems around hydrothermal vents on Earth's ocean floor. These undersea vents on Earth support thriving communities of life in complete darkness, deriving energy from chemical reactions rather than sunlight. Could life exist in Europa's ocean? We don't know, but the conditions may be right. Liquid water is present. Chemical energy may be available, and the environment has been stable for billions of years, potentially long enough for life to arise and evolve. The ice shell itself may play an important role in making Europa potentially habitable. On Earth, ice can trap bubbles of air and organic compounds. On Europa, the constant churning and recycling of the ice shell may transport oxidants, organic materials, and other chemicals from the radiation-processed surface down into the ocean, providing the nutrients that life would need. The radiation at Europa's surface is intense, but not as extreme as at Io. Jupiter's magnetosphere creates a harsh radiation environment that would be lethal to unprotected life on the surface. But just a few centimeters beneath the ice, radiation levels drop dramatically. And in the ocean, dozens of kilometers below, the water itself provides complete shielding from radiation. Understanding Europa's ocean is one of the highest priorities in planetary science. NASA's Europa Clipper mission, launched in 2024, will make dozens of close flybys of Europa, using radar to probe the thickness of the ice shell, analyzing the composition of surface materials, and searching for active plumes. The European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, will also study Europa during its mission to the Jupiter system. Future missions may attempt to land on Europa's surface, and eventually, we may send a probe to melt through the ice and explore the ocean directly. Such a mission would be extraordinarily challenging, requiring autonomous technology capable of navigating beneath kilometers of ice in an alien ocean. But the potential reward, the discovery of life beyond Earth, makes it worth the effort. Europa represents a profound shift in how we think about habitability in the universe. For decades, we assumed that life required a planet in the habitable zone around a star, where temperatures allow liquid water to exist on the surface. But Europa is not in the Sun's habitable zone. It is warmed not by sunlight but by gravitational forces, by the constant tug of Jupiter's immense gravity and the orbital dance with its neighboring moons. This realization has expanded our search for life beyond our solar system. Ocean worlds like Europa may be common throughout the universe, moons orbiting giant planets in the outer reaches of planetary systems, too far from their stars for sunlight to warm them, but kept liquid by tidal heating. The universe may be full of hidden oceans, worlds where life could exist beneath frozen shells, invisible from the outside but potentially teeming with organisms below. As we leave Europa, we carry with us the tantalizing possibility that we are not alone, that life may exist just beneath the ice of this small moon orbiting Jupiter. Our journey continues to the next moon outward, a world that holds its own records. We travel now to Ganymede, the largest moon in the entire solar system. Chapter 6. Ganymede, the giant moon. Beyond Europa lies Ganymede, the largest moon in the solar system. With a diameter of 5,268 kilometers, Ganymede is larger than the planet Mercury and 3/4 the size of Mars. If it orbited the Sun instead of Jupiter, we would classify it as a planet in its own right. Ganymede orbits Jupiter at a distance of 1,070,000 kilometers, taking 7 days and 3 hours to complete one orbit. From Jupiter's cloud tops, it appears as a substantial disk, clearly showing light and dark surface features even to the unaided eye, if one could stand in Jupiter's turbulent atmosphere. Like Europa, Ganymede has a surface dominated by water ice. But unlike Europa's relatively young and smooth surface, Ganymede tells a more complex story, a tale written across billions of years of geological history. Its surface is divided into two distinct terrains that speak to ancient processes and violent events. About 40% of Ganymede's surface consists of dark terrain, ancient cratered regions that date back over 4 billion years to the early days of the solar system. These dark regions are heavily scarred by impact craters, some of them hundreds of kilometers across, recording the intense bombardment that all worlds experienced in the early solar system. The dark material itself may be a mixture of ice and rocky debris, darkened by billions of years of exposure to charged particles from Jupiter's magnetosphere. The remaining 60% of Ganymede's surface is lighter in color and shows a completely different character. These bright regions are grooved terrain, marked by parallel ridges and valleys that can stretch for thousands of kilometers across the moon's surface. These grooves are evidence of tectonic activity, places where Ganymede's ice shell has cracked, shifted, and been resurfaced with cleaner ice from below. The boundary between dark and light terrain is often sharp and dramatic. In some places, grooved terrain appears to have formed when sections of the older, dark crust were pulled apart, with newer ice flooding up from below to fill the gaps. This process, similar to seafloor spreading on Earth, suggests that Ganymede was once geologically active, with a warm interior that drove surface renewal billions of years ago. One of the most striking features on Ganymede is Galileo Regio, a vast dark region over 3,000 kilometers across. This ancient terrain is saturated with impact craters, some of them so old that they have been partially erased by slow relaxation of the ice, like craters slowly filling in and smoothing out over geological time. Within this region lie some of the oldest surfaces in the solar system, windows into the early history of the Jupiter system. But Ganymede's most remarkable feature is not visible on its surface. In 1996, the Galileo spacecraft discovered that Ganymede has its own magnetic field, the only moon in the solar system known to possess one. This magnetic field is generated deep within Ganymede, likely by a liquid iron core at the Moon's center, where convecting molten metal creates electrical currents and generates magnetism. This discovery revealed that Ganymede is not simply a ball of ice and rock. It has a layered internal structure remarkably similar to a terrestrial planet. At the center lies an iron-rich core, possibly as large as 1,500 kilometers in radius. Surrounding this core is a rocky mantle, and above that, multiple layers of ice and water. Like Europa, Ganymede likely harbors an internal ocean, sandwiched between layers of ice at different pressures and temperatures. But Ganymede's ocean is buried much deeper, beneath perhaps 150 kilometers of ice. This ocean may contain more water than Europa's ocean, making it one of the largest reservoirs of liquid water in the solar system. The presence of this ocean has been confirmed by observations of how Ganymede's auroras wobble. Ganymede, like Earth, has auroras near its poles, created when charged particles from Jupiter's magnetosphere interact with Ganymede's magnetic field. By carefully measuring how these auroras move, scientists can infer the presence of a conducting layer beneath the surface. The only material that fits the observations is a salty ocean. However, Ganymede's ocean is likely very different from Europa's. Because it lies beneath so much ice, it may not be in contact with a rocky seafloor. Instead, the ocean might be trapped between layers of ice, with high-pressure ice phases below and normal ice above. This could make it less favorable for life than Europa's ocean, as there would be no rock-water interactions to provide chemical energy. Still, the existence of this ocean raises intriguing possibilities. Water might still interact with rock through cracks and channels in the deep ice. And even without rock contact, other energy sources might be available. Tidal heating, though much weaker at Ganymede than at Europa or Io, could still provide some warmth. And chemical gradients between different ice layers might create environments where unusual forms of life could potentially exist. Ganymede's thin atmosphere is another point of interest. The Moon is surrounded by an extremely tenuous atmosphere of oxygen, created when charged particles from Jupiter strike the ice surface and break water molecules apart. This oxygen atmosphere is about 1 billion times thinner than Earth's atmosphere, essentially a vacuum by our standards, but it represents a dynamic interaction between the Moon and its environment. The surface of Ganymede also shows evidence of past geological activity that we still don't fully understand. Some regions show signs of cryovolcanism, where liquid water or slushy ice erupted onto the surface like lava on Earth. Other areas show strange circular features that may be the scars of ancient impacts that penetrated through the ice shell and released water from below. One of the great mysteries of Ganymede is why its geological activity apparently ceased billions of years ago. The groove terrain was formed between 1 and 2 billion years ago, and since then, the Moon appears to have been largely dormant. Perhaps the heat source that drove its tectonics, whether radioactive decay or tidal heating, gradually diminished until the Moon froze into its current state. Or perhaps changes in the orbital resonances with other moons reduced the tidal heating that once warmed Ganymede's interior. Today, Ganymede is a world frozen in time, preserving in its surface a record of geological processes that occurred when the solar system was young. Its ancient cratered terrain records the impact history of the outer solar system. Its grooved terrain shows us what tectonic processes look like on a world where ice, not rock, forms the crust. And its hidden ocean, buried beneath layers of ice, reminds us that water is abundant in the outer solar system, locked away in forms we are only beginning to understand. Future missions will tell us more about this giant moon. The European Space Agency's JUICE mission will orbit Ganymede, mapping its surface in unprecedented detail, probing the depth and characteristics of its subsurface ocean, and studying its unique magnetic field. These observations may finally reveal whether Ganymede's ocean could harbor life, and what geological processes shaped this world into its current form. As we prepare to leave Ganymede and continue our journey, we move outward to the last of Jupiter's giant moons. Our next destination is a world that, unlike its siblings, appears to have remained almost unchanged since the early days of the solar system. We travel now to Callisto, the ancient survivor. Chapter 7. Callisto, the ancient survivor. Callisto orbits Jupiter at a distance of 1,880,000 kilometers, the outermost of the 4 Galilean moons. It takes 16 days and 16 hours to complete one orbit, moving at a stately pace compared to its inner siblings. From this distant vantage point, it orbits just beyond the most intense regions of Jupiter's radiation belts, making it a somewhat safer environment than the other Galilean moons. Callisto is almost the same size as Mercury, with a diameter of 4,821 kilometers. It is the third largest moon in the solar system, smaller only than Ganymede and Saturn's moon Titan. Yet despite its impressive size, Callisto appears to be frozen in time, a world that has changed little since the early days of the solar system. When we look at Callisto, we see a surface utterly saturated with impact craters. Every available space is marked by the scars of ancient collisions. Large craters overlap smaller ones. Ancient impacts have been partially erased by later impacts. The surface is so heavily cratered that planetary scientists consider it at equilibrium, meaning that any new impact simply erases an older crater, leaving the overall crater density unchanged. This extraordinary crater density tells us that Callisto's surface is ancient, perhaps 4 billion years old, dating back to the period of heavy bombardment when the young solar system was filled with debris and collisions were frequent. While Io continuously renews its surface through volcanism, and Europa and Ganymede have been partially resurfaced by geological activity, Callisto has remained largely unchanged, a cosmic time capsule. The most spectacular feature on Callisto is Valhalla, one of the largest impact structures in the entire solar system. Valhalla consists of a bright central region about 600 kilometers across, surrounded by concentric rings that extend outward for nearly 2,000 kilometers. These rings are scarps and ridges created when the impact sent shockwaves rippling through Callisto's icy shell, like the ripples created when a stone is thrown into water, but frozen in place for billions of years. The impact that created Valhalla must have been catastrophic, perhaps coming close to shattering the entire moon. The projectile that struck Callisto was likely tens of kilometers across, traveling at tens of kilometers per second. The energy released would have been equivalent to millions of nuclear weapons, excavating material from deep within Callisto and briefly melting vast regions of the ice shell. Another large impact structure, Asgard, shows similar ring patterns and spans about 1,700 kilometers. These multi-ring basins are found on several moons and planets, but Callisto's examples are among the best preserved, offering insights into how icy crusts respond to massive impacts. Despite its ancient, battered appearance, Callisto holds secrets beneath its surface. Like Europa and Ganymede, Callisto likely harbors a subsurface ocean. Magnetic field measurements by the Galileo spacecraft revealed evidence of a conducting layer beneath the surface, most consistent with a salty ocean. This ocean is probably buried beneath 100 kilometers or more of ice, making it the deepest and most inaccessible of all the Galilean moon's oceans. But here is Callisto's great puzzle. Why has it remained so geologically dead? Its neighbors have all shown signs of internal activity. Io is constantly being reshaped by volcanism. Europa's surface is young and active. Ganymede was tectonically active for billions of years. Yet Callisto appears to have been frozen solid since the early solar system, never developing the internal heat needed to drive geological processes. The answer may lie in Callisto's orbit. Unlike the inner three Galilean moons, Callisto is not part of the orbital resonance that locks Io, Europa, and Ganymede into their gravitational dance. Without this resonance, Callisto experiences much less tidal heating. Its orbit is nearly circular, so Jupiter's gravity pulls on it uniformly, without the constant flexing and squeezing that generates heat in the inner moons. Without tidal heating, Callisto has cooled primarily through the slow decay of radioactive elements in its interior. This heat was never sufficient to drive vigorous geological activity at the surface. As a result, Callisto's ice shell may be extremely thick, perhaps over 100 kilometers, with the ocean buried far below. This thick ice shell has implications for habitability. While Callisto has liquid water, that water is almost certainly not in contact with rock. The ocean is probably sandwiched between layers of ice, with no rock-water interactions to provide the chemical energy that might support life. Of all the potentially habitable ocean worlds in the Jupiter system, Callisto seems the least promising. Yet Callisto still has value for astrobiology, if not as a habitat, then as a baseline. By comparing Callisto with Europa and Ganymede, we can understand what conditions are necessary for a moon to remain geologically active and potentially habitable. Callisto shows us what happens when tidal heating is absent, when a world simply cools and freezes without the gravitational interactions that warm its siblings. For future human exploration, however, Callisto may be the most attractive destination in the Jupiter system. Its distance from Jupiter means the radiation environment is about 1,000 times less intense than at Europa or Io. A human base on Callisto would require far less shielding, and astronauts could venture onto the surface without immediate danger from radiation. Callisto could serve as a base for exploring the entire Jupiter system. From Callisto's surface, Jupiter appears as a magnificent sphere about the size of Earth's moon as seen from our planet, showing its banded clouds and the shadows of inner moons transiting across its face. The inner Galilean moons would appear as bright stars, Ganymede the brightest, with Europa and Io closer to Jupiter's glare. Water ice is abundant on Callisto, providing resources for life support and rocket fuel. The low radiation means that solar panels could be used for power without rapid degradation. And the weak gravity, only about 1/8 of Earth's, would make it relatively easy to launch missions from Callisto's surface to other destinations in the Jupiter system. The surface itself, while heavily cratered, is relatively flat in most regions. There are no towering mountains or deep canyons. The ice is hard and solid, providing a stable foundation for structures. Temperatures are extremely cold, around -139 degrees Celsius, but no colder than other locations in the outer solar system where we might one day establish outposts. Callisto's story is one of patience and preservation. While its neighbors have been transformed by geological forces, Callisto has waited, largely unchanged, for 4 billion years. Its surface is an archive of the early solar system, recording impact events from an era when the planets were young and the solar system was still taking shape. Every crater on Callisto is a piece of history. The large projectiles that created Valhalla and Asgard may have been fragments left over from the formation of the planets themselves. The smaller craters record the continuous rain of debris that all worlds experienced during the heavy bombardment period. By studying these craters, we can reconstruct the impact history of the entire Jupiter system. As we prepare to leave Jupiter and its magnificent family of moons, we carry with us an appreciation for the incredible diversity we have witnessed. 4 large moons, all similar in size, yet each telling a completely different story. Io, tortured by tidal forces into a volcanic hell. Europa, hiding a vast ocean beneath its icy shell. Ganymede, the giant with its own magnetic field and ancient tectonic features. And Callisto, the patient observer, preserving in its surface a record of the early solar system. But our journey is not yet complete. Beyond Jupiter lies another giant planet, adorned with magnificent rings and accompanied by its own remarkable family of moons. We travel now to Saturn, the jewel of the solar system, and its diverse collection of satellites. Chapter 8. Saturn, a realm of icy moons. As we leave Jupiter behind and journey deeper into the outer solar system, we cross nearly 650 million kilometers of space before we encounter the next giant planet. Saturn, the ringed world, orbits the Sun at a distance of 1.4 billion kilometers, taking 29 Earth years to complete a single orbit around our star. Saturn is nearly as large as Jupiter, but less dense. In fact, Saturn's average density is less than water, meaning that if you could find an ocean large enough, Saturn would float. This low density tells us that Saturn is composed primarily of hydrogen and helium, with only a small rocky core at its center, buried beneath thousands of kilometers of metallic hydrogen and gas. But it is Saturn's ring system that captures the imagination. Extending hundreds of thousands of kilometers from the planet, yet remarkably thin, often less than 10 meters thick, these rings are composed of countless particles of ice and rock, ranging in size from grains of sand to house-sized boulders. They catch the sunlight and shine with a brilliance that has enchanted observers since Galileo first glimpsed them through his telescope in 1610. The rings are likely the remnants of a moon that wandered too close to Saturn and was torn apart by tidal forces, or perhaps the debris from a collision between moons. They are not permanent features. Slowly but steadily, the rings are raining down onto Saturn, and in perhaps 100 million years, they may disappear entirely. We are fortunate to live in an era when Saturn wears its magnificent rings. But as spectacular as the rings are, Saturn's moons are equally fascinating. Saturn has at least 146 known moons, more than any other planet. Most are small, irregular chunks of rock and ice, captured asteroids, or fragments from larger moons. But among this crowd are several moons of exceptional interest, worlds that rival the Galilean moons of Jupiter in their complexity and scientific importance. The moons of Saturn are generally icier than Jupiter's moons. At Saturn's distance from the Sun, temperatures are even colder, and water ice is as hard as rock. Many of Saturn's moons are predominantly water ice with only small amounts of rocky material. This gives them bright, reflective surfaces and creates geological processes quite different from those on rocky worlds. Saturn's major moons were discovered over several centuries. Christian Huygens discovered Titan, the largest, in 1655. Giovanni Cassini discovered 4 more moons, Iapetus, Rhea, Tessis, and Dione, between 1671 and 1684. William Herschel found Mimas and Enceladus in 1789. And many smaller moons have been discovered by spacecraft missions, particularly the Cassini spacecraft, which orbited Saturn from 2004 to 2017. The Cassini mission revolutionized our understanding of Saturn and its moons. Over 13 years, Cassini returned hundreds of thousands of images and made countless discoveries. It revealed that Enceladus has geysers erupting from its south pole, shooting water into space. It showed that Titan has lakes and seas of liquid methane on its surface. It discovered new moons and provided detailed views of familiar ones. The data from Cassini will keep scientists busy for decades. Among Saturn's many moons, two stand out as worlds of extraordinary interest, places that may fundamentally change how we think about life in the universe. The first is Titan, larger than Mercury, the only moon with a thick atmosphere, a world where methane takes the place of water in an alien weather cycle. The second is Enceladus, a small, bright moon that may have all the ingredients necessary for life beneath its icy shell. We will explore each of these remarkable worlds in turn, beginning with the largest moon in the Saturn system, and the second largest moon in the entire solar system. We journey now to Titan, a world shrouded in orange haze, where the rain is methane and lakes of hydrocarbons dot the polar regions. Chapter 9. Titan, the world of lakes and rain. Titan orbits Saturn at a distance of 1,200,000 kilometers, taking just under 16 days to complete one orbit. With a diameter of 5,150 kilometers, it is larger than the planet Mercury and only slightly smaller than Jupiter's moon Ganymede. But Titan's most remarkable feature is not its size, but its atmosphere. Titan is the only moon in the solar system with a substantial atmosphere. While other moons have thin traces of gas around them, Titan's atmosphere is thick and dense, with a surface pressure 1.5 times that of Earth's atmosphere at sea level. If you stood on Titan's surface, you would feel more atmospheric pressure than you do on Earth, though you would certainly need a spacesuit as the atmosphere is not breathable and the temperature is -179 degrees Celsius. The atmosphere is composed primarily of nitrogen, about 95%, similar to Earth's atmosphere. The remaining 5% is mostly methane, with small amounts of hydrogen and complex organic molecules. This methane is the key to understanding Titan's unique weather and surface processes. On Earth, water evaporates from the oceans, rises into the atmosphere, forms clouds, and falls back to the surface as rain, flowing in rivers back to the oceans. This water cycle shapes our planet's surface and climate. On Titan, methane plays the same role that water plays on Earth. Methane evaporates from lakes, forms clouds, falls as rain, carves channels in the surface, and flows back to the lakes, completing a methane cycle that is unique in the solar system. From space, Titan appears as a featureless orange sphere. The thick atmosphere is filled with a photochemical haze, created when methane high in the atmosphere is broken apart by sunlight and recombines into complex organic molecules. These molecules form tiny particles that scatter light, giving Titan its characteristic orange color and completely obscuring the surface from view in visible light. It was only when the Cassini spacecraft arrived at Saturn and used radar and infrared instruments to peer through the haze that we finally saw Titan's surface. What those instruments revealed was astonishing: a world shaped by familiar processes operating in alien materials. Titan's surface is diverse and complex. There are vast dune fields near the equator, where wind-blown particles have formed linear dunes hundreds of kilometers long. These dunes are not made of sand, but of small particles of organic material, hydrocarbons that have rained out of the atmosphere over millions of years. The dunes are shaped by winds in Titan's lower atmosphere, creating patterns remarkably similar to sand dunes in Earth's deserts. In the mid-latitudes, the surface is dominated by rough, icy terrain, likely water ice bedrock carved by methane rain. There are networks of channels that look remarkably like river valleys on Earth, carved by flowing liquid. But this liquid is not water. It is methane and ethane, flowing down from higher elevations during Titan's occasional rainstorms. Most spectacular are Titan's polar regions, where radar images revealed something no one had expected: lakes and seas. In Titan's North Polar region, there are 3 large seas and dozens of smaller lakes, filled with liquid hydrocarbons. The largest, Kraken Mare, is larger than the Caspian Sea on Earth, covering about 400,000 square kilometers. Ligeia Mare and Punga Mare are smaller, but still substantial bodies of liquid. These are not lakes of water. The temperature on Titan is far too cold for liquid water. Instead, these lakes and seas are filled with liquid methane and ethane, with dissolved nitrogen and other hydrocarbons. The liquid is incredibly cold by our standards, around -180 degrees Celsius, but at that temperature and under Titan's atmospheric pressure, methane and ethane are liquid, just as water is liquid on Earth. The Cassini spacecraft observed changes in these lakes over the course of its mission. Some lakes appeared to grow or shrink, suggesting seasonal variations in liquid levels. Radar observations detected waves on the surfaces of the larger seas, tiny ripples driven by winds in Titan's lower atmosphere, and specular reflections, the glint of sunlight reflecting off smooth liquid surfaces, confirmed that these are indeed liquid bodies, not just dry lake beds. In January of 2005, the Cassini mission achieved something remarkable. It released a small probe, called Huygens, named after Titan's discoverer, which descended through Titan's atmosphere and landed on the surface. During its 2.5-hour descent, Huygens took hundreds of images and made measurements of the atmosphere and surface. The images from Huygens revealed a landscape that looks hauntingly familiar yet utterly alien. The surface is covered with rounded pebbles, likely made of water ice as hard as rock at Titan's temperatures. There are what appear to be drainage channels leading to darker regions that might be lake beds or dried stream valleys. The sky is a dim orange, with sunlight barely penetrating the thick haze. The surface is dark, receiving only about 1% of the sunlight that reaches Earth's surface. Huygens landed in what appeared to be a dry lake bed or floodplain. The surface was slightly soft, perhaps covered in a layer of organic mud, but with a harder subsurface beneath. The probe operated for over an hour on the surface, transmitting data back to Cassini as it orbited above, a remarkable achievement for a probe designed primarily for the descent through the atmosphere. The atmosphere of Titan has another remarkable characteristic. It is filled with complex organic molecules. These molecules form in the upper atmosphere when sunlight breaks apart methane and nitrogen, and the fragments recombine into increasingly complex chains and rings. Some of these molecules are precursors to amino acids and nucleotide bases, the building blocks of life as we know it. On Titan's surface, these organic molecules accumulate over time, like snow falling from the sky. Over millions of years, this organic rain has built up deposits of complex hydrocarbons across Titan's surface. In some ways, Titan is a natural laboratory for studying prebiotic chemistry, the kinds of chemical reactions that may have led to the origin of life on Earth billions of years ago. However, Titan's surface is far too cold for life as we know it. At -179 degrees Celsius, chemical reactions occur extremely slowly. Water is frozen as hard as granite, and there is no liquid water at the surface where biochemistry could operate. But beneath Titan's surface, conditions may be very different. Like many large moons, Titan likely has a subsurface ocean of liquid water, buried beneath perhaps 50 kilometers of ice. This ocean would be kept liquid by a combination of residual heat from Titan's formation, radioactive decay, and possibly tidal heating from Saturn. If this ocean exists, and if it is in contact with a rocky core at Titan's center, it could provide an environment where life might exist. Water would be liquid, chemical energy would be available from rock-water interactions, and the environment would have been stable for billions of years. This hidden ocean beneath the ice would be completely separate from the methane cycle occurring at the surface, a secret water world beneath an alien landscape. Recent analysis of Cassini's data has provided evidence for this subsurface ocean. Measurements of how Titan's shape changes as it orbits Saturn, due to tidal forces, suggest that there is a liquid layer beneath the surface. And the way radio signals pass through Titan indicates layering consistent with ice, liquid water, and a rocky core. Future missions to Titan are being planned. NASA's Dragonfly mission, scheduled to launch in the late 2020s, will send a drone to explore Titan's surface. This rotorcraft will fly from site to site, landing to analyze the composition of surface materials and search for evidence of prebiotic chemistry. Dragonfly will visit multiple locations, including organic dunes and the site of a potential ice volcano, building a comprehensive picture of Titan's complex chemistry. Titan represents a profound puzzle in astrobiology. At the surface, it is too cold for life as we know it, but it has all the organic chemistry that might be necessary for life. Beneath the surface, it may have a warm water ocean where life could potentially exist, but isolated from the organic-rich surface. Understanding whether these two realms ever connect, whether organic material from the surface ever reaches the subsurface ocean, is key to assessing Titan's habitability. Even if Titan is lifeless, it offers a window into processes that may have occurred on early Earth. The thick atmosphere, the complex organic chemistry, the interaction between liquids and surfaces, all of these may parallel conditions on our own planet billions of years ago, before life arose. By studying Titan, we may learn about our own origins. As we prepare to leave Titan, we carry with us images of a world both alien and strangely familiar. A world where methane rain falls from orange skies, where seas of liquid hydrocarbons lap against shores of ice, where organic molecules accumulate like snow, and where beneath it all, a hidden ocean may hold secrets yet to be discovered. Our journey through Saturn's system continues. We descend now towards Saturn itself, to a small, bright moon that has surprised scientists with its activity and potential. We travel to Enceladus, a world of ice and geysers. Chapter 10. Enceladus, the icy geyser world. Enceladus orbits Saturn at a distance of 238,000 kilometers, closer to Saturn than Titan, but still outside the planet's magnificent rings. It is a small moon, only 504 kilometers in diameter, small enough to fit comfortably within the borders of Arizona. Yet this tiny world has proven to be one of the most scientifically exciting bodies in the entire solar system. Enceladus was discovered in 1789 by William Herschel, the astronomer who also discovered the planet Uranus. For over 2 centuries, it was just another small, icy moon, unremarkable among Saturn's many satellites. But when the Cassini spacecraft arrived at Saturn in 2004, everything changed. From a distance, Enceladus appears as a brilliant white sphere, the brightest object in the solar system. It reflects nearly 100% of the sunlight that hits it, giving it an albedo higher than fresh snow. This extraordinary brightness is due to its surface, which is covered in pristine water ice, constantly being renewed by a process that would soon be discovered. During an early flyby, Cassini's instruments detected something unexpected. As it passed near Enceladus, the spacecraft detected a cloud of water vapor. At first, scientists thought this might be an instrument error or perhaps material from Saturn's rings. But as Cassini made closer approaches, the truth became clear. Enceladus was actively venting water into space. The source of this water was Enceladus's south polar region. Images revealed a series of parallel fractures, nicknamed tiger stripes, each about 130 kilometers long and separated by about 35 kilometers. These fractures are warmer than the surrounding terrain, and from them, jets of water vapor and ice particles shoot hundreds of kilometers into space. These are not occasional outbursts. The geysers are erupting continuously, ejecting about 200 kilograms of material per second into space. This is enough material to create a faint atmosphere around Enceladus and to supply Saturn's E-ring, a tenuous ring of tiny ice particles that extends from inside the orbit of Mimas to beyond the orbit of Titan. The discovery of active geysers on such a small moon was astonishing. Moons this small should have cooled off long ago, becoming geologically dead. Yet here was Enceladus, actively venting material from its interior, clearly possessing internal heat and possibly liquid water. Cassini flew through these plumes multiple times, analyzing their composition. The instruments detected water vapor, ice particles, carbon dioxide, methane, ammonia, and complex organic molecules. Most intriguingly, the spacecraft detected molecular hydrogen, a finding that has profound implications for the potential habitability of Enceladus. Molecular hydrogen is produced when hot water reacts with rock, a process called serpentinization that occurs at hydrothermal vents on Earth's ocean floor. The presence of hydrogen in Enceladus's plumes strongly suggests that there are hydrothermal vents on the floor of Enceladus's subsurface ocean, where water at around 90 degrees Celsius or warmer is reacting with rock, releasing hydrogen and chemical energy. On Earth, life thrives around hydrothermal vents in the deep ocean, deriving energy from the chemical reactions occurring there. These ecosystems exist in complete darkness, independent of sunlight, powered purely by geochemistry. The discovery of similar conditions on Enceladus makes it one of the most promising places in the solar system to search for life. The ocean beneath Enceladus's ice shell is global, meaning it surrounds the entire moon beneath the ice. The ice shell is estimated to be 20 to 30 kilometers thick on average, though it is much thinner at the South Pole where the geysers erupt. The ocean itself may be 10 kilometers or more in depth, containing a volume of water comparable to Lake Superior on Earth. This ocean is kept liquid by tidal heating. Enceladus is locked in an orbital resonance with another of Saturn's moons, Dione. This resonance causes Enceladus's orbit to be slightly elliptical, and as it moves closer to and farther from Saturn, tidal forces flex and heat its interior. The heating is concentrated at the South Pole due to the specific geometry of the tidal forces and the internal structure of the Moon. The tiger stripe fractures at the South Pole are the conduits through which ocean water reaches the surface. The exact mechanism is still debated, but it appears that tidal forces periodically widen these fractures, allowing pressurized water from the ocean below to rush upward. As this water reaches the vacuum of space, it explosively boils, creating the plumes we observe. The south polar region of Enceladus is about 30 degrees warmer than it should be based on sunlight alone, with temperatures reaching about -130 degrees Celsius in some areas. This warmth comes from below, from the ocean and the tidal heating that warms Enceladus's interior. Infrared images show that the tiger stripes glow with heat, like cracks in the surface of a frozen world revealing the warmth beneath. The geysers appear to vary in intensity with Enceladus's orbital position. When Enceladus is farthest from Saturn in its elliptical orbit, tidal forces are weaker, and the fractures close slightly, reducing the eruption rate. When Enceladus is closest to Saturn, tidal forces are strongest, the fractures open wider, and the geysers erupt more vigorously. Cassini observed these variations, confirming that the geysers are directly linked to tidal forces. The surface of Enceladus tells a story of geological activity both past and present. The northern and equatorial regions are heavily cratered, ancient terrain dating back billions of years. But the south polar region is almost devoid of craters, indicating that the surface there is very young, perhaps only tens of millions of years old. The geysers continuously deposit fresh ice on the surface, erasing craters and creating the smooth, bright terrain we see. Other parts of Enceladus show signs of past geological activity. There are tectonic features, fractures and ridges indicating that the Moon's surface has been stressed and deformed. Some regions show evidence of past resurfacing, where liquid water or slushy ice erupted onto the surface and froze, creating smooth plains. The interior structure of Enceladus is fascinating. At the center is a rocky core, probably about 200 kilometers in radius. This core is in contact with the liquid water ocean, allowing the rock-water interactions that produce hydrogen. Above the ocean is the ice shell, thinner at the South Pole and thicker elsewhere. The total picture is of a moon with a geologically active interior, driven by tidal heating. For astrobiology, Enceladus checks nearly every box on the habitability checklist. It has liquid water, confirmed by the geysers. It has organic molecules, detected in the plume. It has an energy source, the chemical reactions between water and rock that produce hydrogen. It has a stable environment that has existed for potentially billions of years. And remarkably, it offers direct access to this ocean through the plumes, meaning we can sample ocean water without having to drill through kilometers of ice. Future missions to Enceladus are being seriously considered. A spacecraft could fly through the plumes repeatedly, collecting samples and analyzing them for complex organic molecules, amino acids, or even evidence of life itself. A more ambitious mission might land near the South Pole and analyze the fresh ice deposited by the geysers. And eventually, we might send a probe into the ocean itself, entering through one of the tiger stripe fractures to explore this alien sea. The discovery that such a small moon can harbor a habitable ocean has revolutionized our thinking about where life might exist. We no longer need to limit our search to planets in habitable zones around stars. Moons throughout the outer solar system, warmed by tidal forces rather than starlight, may be far more common habitats for life than Earth-like planets. Enceladus, this tiny, brilliant moon orbiting Saturn, may be one of the most important worlds in the solar system. Its geysers are a gift to science, allowing us to sample an alien ocean without landing on the surface. Its potential for harboring life makes it a priority target for future exploration. And its very existence reminds us that even the smallest worlds can hold the greatest surprises. As we prepare to leave Saturn and journey to the distant reaches of the outer solar system, we carry with us the knowledge that ocean worlds are common, that small moons can be geologically active, and that life might exist in places we never imagined. Our journey continues outward, to the ice giants Uranus and Neptune, and to the distant worlds beyond. Chapter 11. The Distant Moons, Uranus, Neptune, and beyond. Beyond Saturn, the solar system grows cold and dark. Sunlight at these distances is faint, providing only a fraction of the warmth and illumination that we receive on Earth. Yet even here, in the outer reaches of the solar system, we find moons, strange worlds shaped by unique histories and bizarre characteristics. Uranus, the ice giant, orbits at a distance of 2.8 billion kilometers from the Sun. It takes 84 Earth years to complete one orbit. Uranus is unique among the planets because it rotates on its side, with its axis of rotation tilted 98 degrees from vertical. This extreme tilt means that Uranus essentially rolls around the Sun, and its poles experience 42 years of continuous sunlight followed by 42 years of darkness. This unusual orientation affects Uranus's moons as well. The major moons orbit in the plane of Uranus's equator, meaning their orbits are nearly perpendicular to the plane of the solar system. As Uranus moves around the Sun, these moons experience extreme seasonal variations, with one pole pointing toward the Sun for decades at a time. Uranus has 27 known moons, named after characters from the works of William Shakespeare and Alexander Pope, a unique naming convention among planetary satellites. The largest of these is Titania, with a diameter of 1,578 kilometers, followed by Oberon, Umbriel, Ariel, and Miranda. Most of our knowledge about Uranus's moons comes from a single encounter, the Voyager 2 flyby in 1986. Voyager 2 is the only spacecraft to have visited Uranus, and its brief passage through the system provided our only close-up views of these distant worlds. The most remarkable of Uranus's moons is Miranda, the smallest of the 5 major satellites. Miranda is only 471 kilometers in diameter, yet its surface is among the most bizarre in the solar system. It appears as if several different types of terrain have been haphazardly stuck together, creating a patchwork world. There are regions of ancient, heavily cratered terrain next to areas of grooved and ridged surfaces. Most dramatically, there are coronae, large regions bounded by sharp cliffs and filled with parallel ridges and valleys. One of these cliffs, Verona Rupes, is estimated to be 20 kilometers high, the tallest known cliff in the solar system. On Miranda's low gravity, an object dropped from the top would take about 12 minutes to reach the bottom. The origin of Miranda's chaotic appearance is still debated. One hypothesis suggests that Miranda was shattered by a massive impact and then reassembled, with the pieces not quite fitting back together properly. Another suggests that tidal heating, perhaps during a time when Miranda was in orbital resonance with other moons, drove intense geological activity that created the different terrains. The truth may involve elements of both processes. The other major moons of Uranus show their own intriguing features. Ariel has the brightest and possibly youngest surface, with evidence of past geological activity including faults and valleys that may have been carved by flowing liquids, possibly liquid ammonia or water mixed with ammonia. Umbriel is the darkest of the major moons. Its ancient, heavily cratered surface suggesting little geological activity. Titania and Oberon are similar in appearance, with a mix of impact craters and evidence of past tectonic activity. Moving farther out, we come to Neptune, the outermost planet. Orbiting at 4.5 billion kilometers from the Sun, Neptune takes 165 years to complete one orbit. Like Uranus, Neptune is an ice giant, composed primarily of water, methane, and ammonia ices surrounding a rocky core, with an atmosphere of hydrogen and helium. Neptune has 14 known moons. The largest, Triton, is exceptional not only among Neptune's moons, but among all moons in the solar system. Triton is the seventh largest moon, with a diameter of 2,700 kilometers, larger than Pluto. But what makes Triton truly unique is its orbit. Triton orbits Neptune in a retrograde direction, meaning it orbits opposite to Neptune's rotation. This is highly unusual. All major moons that formed alongside their planets orbit in the same direction the planet rotates. A retrograde orbit indicates that Triton did not form with Neptune but was captured, likely from the Kuiper Belt, the region of icy bodies beyond Neptune's orbit. Triton is probably a captured dwarf planet, similar in many ways to Pluto. The capture event must have been dramatic, likely involving a collision or near-miss with another moon. The initial orbit after capture would have been highly elliptical, and tidal forces gradually circularized it over millions of years, generating tremendous heat in the process. This tidal heating may have completely melted Triton, differentiating its interior and erasing any geological features from before the capture. Today, Triton has a relatively young surface, with few impact craters, indicating geological activity within the last 100 million years or so. Voyager 2 flew past Triton in 1989, providing our only close-up images. The spacecraft revealed a surface of frozen nitrogen, with polar caps of nitrogen and methane ice. The surface is marked by strange features including long, narrow ridges and a rough terrain nicknamed cantaloupe terrain because it resembles the skin of a melon. Most remarkably, Voyager discovered active geysers on Triton. These are not geysers of water like on Enceladus, but eruptions of nitrogen gas and dark organic material. Sunlight warms nitrogen ice just beneath Triton's surface, causing it to sublimate into gas. This gas builds up pressure until it breaks through the surface, erupting in a geyser that can shoot material 8 kilometers high. The winds in Triton's thin atmosphere then carry this material downwind, creating dark streaks across the surface. Triton is gradually spiraling inward toward Neptune. Tidal forces are slowly robbing energy from its orbit. In perhaps 1 to 3 billion years, Triton will cross the Roche limit and be torn apart by Neptune's gravity, potentially creating a spectacular ring system around Neptune that could rival or surpass Saturn's rings. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies left over from the formation of the solar system. Here we find Pluto, once considered the 9th planet, now classified as a dwarf planet, along with many similar objects. Pluto has 5 known moons, the largest being Charon. Charon is unusual because it is so large relative to Pluto. With a diameter about half that of Pluto, the Pluto-Charon system is sometimes considered a double dwarf planet. The two worlds are tidally locked to each other, meaning they always show the same face to each other as they orbit their common center of mass. The New Horizons spacecraft flew past Pluto and Charon in 2015, revealing worlds of unexpected geological diversity. Charon has a relatively smooth southern hemisphere and a more varied northern hemisphere with canyons, mountains, and evidence of past cryovolcanism, where water ice or ammonia ice erupted onto the surface. These distant moons remind us that even in the cold, dark outer reaches of the solar system, worlds can be geologically active and complex. They challenge our assumptions about what drives geological processes and where we might find interesting environments. They are the frontier of our exploration, the edge of the known solar system, and beyond them lie countless other moons orbiting dwarf planets and other objects, most of which we have never seen up close. As we conclude our survey of the solar system's moons, we turn our gaze toward the future, to the missions that will explore these worlds in greater detail, and to the questions that drive us to continue this journey of discovery. Chapter 12. The Future of Moon Exploration. We have journeyed through the solar system, visiting moons both familiar and strange. We have walked on the cratered plains of Earth's moon and witnessed the volcanic fury of Io. We have contemplated the hidden oceans of Europa, Ganymede, and Enceladus, and marveled at the methane lakes of Titan. We have seen ancient worlds like Callisto that preserve the memory of the early solar system, and discovered that even the smallest moons can harbor active geology and potentially habitable environments. What have we learned from this journey? Perhaps most importantly, we have learned that moons are not just passive companions to planets, but complex worlds in their own right, shaped by diverse processes and potentially harboring environments suitable for life. We have learned that liquid water is common in the outer solar system, not as liquid oceans on the surface, but hidden beneath ice shells, warmed by tidal forces and radioactive decay. These subsurface oceans may be among the most common habitable environments in the universe, far more abundant than Earth-like planets with surface oceans. We have learned that geological activity can persist for billions of years, even on small worlds, when tidal heating provides a continuous energy source. The dance of gravitational forces between moons and planets creates internal heat that drives volcanism, tectonics, and the maintenance of subsurface oceans. We have learned that atmospheres are rare among moons, with only Titan possessing a substantial atmosphere. Yet this rarity makes Titan all the more valuable as a natural laboratory for studying atmospheric processes and organic chemistry. And we have learned that the solar system is far more dynamic and interesting than we once believed. Every moon tells a story. Some stories speak of ancient processes, frozen in time. Others speak of ongoing activity, of worlds that are alive in a geological sense. And a few stories whisper the tantalizing possibility that we might not be alone, that life might exist in the hidden oceans of icy moons. Looking to the future, the exploration of moons is entering an exciting new phase. Multiple missions are planned or under development to study the most promising targets in our search for life and understanding of planetary processes. NASA's Europa Clipper mission, launched in 2024, will make dozens of close flybys of Europa, using radar to probe the ice shell, analyzing the composition of surface materials, measuring the thickness and salinity of the subsurface ocean, and searching for active plumes. The data from Europa Clipper will help us understand whether Europa's ocean is habitable and will guide the design of future missions that might land on the surface or even explore the ocean directly. The European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, will study Ganymede, Callisto, and Europa, eventually entering orbit around Ganymede to conduct detailed studies of this giant moon. JUICE will help us understand the formation and evolution of icy moons and assess the habitability of their subsurface oceans. NASA's Dragonfly mission, scheduled to launch in the late 2020s, will send a rotorcraft to Titan. This drone will fly from site to site, landing to analyze surface materials and search for complex organic molecules. Dragonfly will visit regions where liquid methane may have mixed with surface materials, potentially creating environments favorable for prebiotic chemistry. Future missions to Enceladus are being studied, with concepts ranging from orbiters that would repeatedly fly through the plumes to landers that would analyze fresh ice near the South Pole. Some concepts even envision a probe that would melt through the ice and enter the subsurface ocean directly, a mission of extraordinary complexity but immense scientific value. For more distant targets like Tritown and the moons of Uranus, missions are in the early planning stages. These worlds have been visited only once, briefly, by Voyager 2. Orbiter missions to Uranus or Neptune would revolutionize our understanding of these systems, just as Cassini transformed our knowledge of Saturn. Beyond robotic exploration, there is growing interest in human missions to some moons. Earth's moon is the primary near-term target, with NASA's Artemis program aiming to establish a sustainable human presence on the lunar surface. The lessons learned from lunar operations will inform future missions to more distant destinations. In the longer term, Callisto has been proposed as a potential base for human exploration of the Jupiter system. Its lower radiation environment compared to the inner Galilean moons makes it more suitable for human habitation. From Callisto, astronauts could operate robotic missions to Europa and the other moons, conduct scientific research, and perhaps one day travel to the surfaces of these worlds themselves. The moons of our solar system also have implications for the search for life beyond our solar system. The discovery that ocean worlds are common has expanded the concept of habitable zones. We now understand that a planet or moon does not need to be at the right distance from its star to have liquid water. Tidal heating from orbital interactions can maintain habitable conditions far from the warmth of a star. This means that in other planetary systems, moons orbiting giant planets could be habitable, even if those planets are far from their stars. The number of potentially habitable worlds in the universe may be far greater than we previously thought. Every giant planet might host a family of moons, some of which could harbor life in subsurface oceans. The study of moons also helps us understand planetary formation and evolution. Moons are time capsules, preserving records of processes that occurred billions of years ago. By studying ancient surfaces like Callisto's, we can reconstruct the impact history of the solar system. By comparing geologically active moons like Io and Enceladus with dormant moons like Callisto, we can understand what factors drive or prevent geological activity. The diversity of moons challenges our theories and expands our understanding. Each new discovery forces us to refine our models and sometimes to completely reconsider what we thought we knew. This is the essence of science, the willingness to change our understanding in the face of new evidence. As we conclude this journey through the moons of our solar system, we are left with a sense of wonder and curiosity. These worlds, from the familiar moon in our night sky to distant Tritown in the outer reaches of the solar system, are part of our cosmic family. They formed from the same cloud of gas and dust that gave birth to the sun and planets. They have evolved over billions of years, shaped by gravity, heat, and chemistry. Some moons may harbor life, making them perhaps the most important worlds in the solar system for astrobiology. Others are natural laboratories where we can study processes that operate throughout the universe. All of them expand our perspective, reminding us that we live in a solar system rich with diverse worlds, each with its own story to tell. The exploration of moons is a journey that has only just begun. We have sent spacecraft to only a fraction of the known moons, and there are surely many more moons yet to be discovered orbiting the outer planets and dwarf planets. Each future mission will bring new surprises, new discoveries, and new questions. Perhaps one day, humans will stand on the surface of Europa, looking out across a frozen plain toward the massive disk of Jupiter hanging in the black sky, or walk through the orange haze of Titan, rain of liquid methane pattering on their suits, or gaze at the geysers of Enceladus, plumes of water shooting into space against the backdrop of Saturn's rings. These visions of the future inspire us to continue exploring, to keep sending our robotic emissaries to these distant worlds, and to prepare for the day when humans follow. The moons of our solar system are waiting, each one a world of wonders, each one holding secrets that will take generations to uncover. As you drift off to sleep or continue your studies, perhaps you will dream of these alien worlds. Perhaps you will imagine standing on the icy plains of Europa or flying through the skies of Titan. Perhaps you will wonder what it would be like to witness Io's volcanic eruptions, or to see the rings of Saturn from the surface of Enceladus. The moons of our solar system remind us that we live in a universe of infinite variety and beauty, where every world is unique, where mysteries abound, and where the journey of discovery never ends. From our own moon, which has watched over humanity since the dawn of our species, to the distant moons circling Neptune at the edge of the solar system, these worlds are part of our cosmic heritage. The exploration continues. The questions remain. The moons await. And the universe, with all its wonders, invites us to keep looking up, keep wondering, and keep exploring. Good night, and may your dreams carry you to distant moons under alien skies.